This is video on kinematics of particle. It is the 9th video in this series wherein we are looking at the work energy principle, and we are going to use this principle to solve problems of kinematics of particle. And in this particular video, that is video 3, we are looking at system of particles, that is number of particles when they are connected together by a string. How do you handle that? That we are going to see in this video. Now, even if there is a system of particles, our energy equation, which was explained in our video 6 of this series, part 6, holds. Only you have to carefully understand few things. That is, while working out MGH, for each particle, you have to take independent reference. Means, while working out MGH, take independent reference for each body or each particle. Then, take MGH half mv square half kx square for each particle together in a group for system of particles. So see, we are dealing with system of particles. So in this case, the energies for all particles have to be grouped into this. And third is, add up energy lost in friction for all the particles. So see, friction into distance, this term contains and for all the particles, whatever energy is lost, that should be included in this term. Now these points will become more clear as soon as we look at the problems. So let's look at the first problem. It says two blocks A and B of masses 100 and 150 kg are connected by string. If the system is released from rest, find velocity of block A after it has moved a distance of 1 meter. Assume the coefficient of friction between the block A and the horizontal plane as 0.2. Now you see, this connected system is in position 1 at the moment and it is at rest, and then A moves by 1 meter, naturally B will come down by 1 meter, and that will be its position 2. That will be its position 2. Few things you have to assume. The string is inextensible, pulley is frictionless, and this distance here on the plane is sufficient so that A won't fall off or hit the pulley. Now let's use our energy balance equation. Now there is no external force, so F into D is 0. Now we will take, for the purpose of MGH, we will take reference for A as this plane and reference for B as this level. Now since both of them in position 1 are at their own references, MGH is 0. Half mv square for both bodies is 0 because it's starting from rest and there is no spring, therefore half kx square is 0. Now in second position, when A moves towards right and B goes down, MGH for A is not changed. It continues to be 0 because it's still at its own reference. But if B goes down by 1 meter and it's negative as it's lost the height, and therefore this is its therefore this total is its MGH, and that's what we meant in the previous slide by taking the potential energies together. Means the potential energy of A and B are taken together in a bracket, and that's called MGH. Similarly, we are going to take both kinetic energies and put for this term. So it is half mv square, masses added, and common v because they are connected by this simple string. Half kx square 0, no spring, and friction into distance. Distance is 1, and friction is only applied to body A, because B doesn't touch anything. So B's friction term is not there, only A's frictional term is there. Frictional force is 0.2 R, R is 100 G, the weight, and into 1. And then, since it has only one unknown, we can work out V as 3.19 meter per square at the end of the 1 meter. Okay, let's look at next problem. It says, system of 3 particles is pulled by a force P as shown. The system starts from rest and achieves velocity of 3 meter per second when entire system moves by 4.5 meter. So in the direction of P, all these are going to move by 4.5 meters. If coefficient of friction for all contact surfaces is 0.3, we are required to find the force P. So what do? We write energy equation. We realize that there is external force F and P moved by 4.5. So P into 4.5 is the external work done. Now initially wherever they are, that will be the reference level for each of the bodies, and therefore mgh in first position where it is at rest is 0, half mv square is 0 because system is at rest, and half kx square is 0 because there is no spring. Now on the right hand side, that is after the entire system has moved by 4.5 meter, what we'll find is 250 and 500 won't leave the level, respective levels. We have to assume that. So no change in energy. But this 1000 meter will move up the plane by 4.5 meter. It means it will gain height of 4.5 into sine 53.13. If this 4 by 3, from that 53.13 angle comes. So this mgh term contains this only potential energy gained by 1000. Then half mv square, see, all these have achieved velocity of 3. 1750 is the total mass and half mv square. 1750 by g is the total mass, and then is half mv square, the kinetic energy term. No spring, so 0. And friction into dc, for each body has lost some energy in friction. That you have to take together for this term. So it is for 500, it is R, this is R, for R is 500, mu R is frictional force into 4.5. Similarly for 250, it is 0.3 into 250 into 4.5. And for 1000, the R is 1000 cos 53.13. Frictional force is mu R, 0.3 into this. There is 0.3 into 1000 cos 53.13, and the distance traveled is 4.5. So the total energy, friction energy, is put in this, and here this equation has only one unknown, and therefore we can easily solve for P. Next, the last problem goes like this. A force P of 14 Newton is applied to the system, which is initially at rest. Determine the speeds of A and B after A has moved 0.4 meter. We do similar exercise, but we settle the tension. See, same string will have same tension, so T, T, T going like this, but this string will have twice of T, this because it has to balance out these two T's. So in other words, this 10 kg is pulled by T, 6 kg is pulled by 2T. In our energy balance equation, we write F into D. So F is 40 and D we have written, mind you, as 0.8. Whereas A has moved by 0.4, so B will move by 0.8. Reason we'll explain in a minute. Now mgh for both is 0, half mv square 0 initially, half kx square 0 initially. I mean no spring, so initially and later also is 0. After it has moved by that distance, mgs continues to be 0 because they have not left their position. Half mv square will be there, and we'll find v, and half kx square is 0. Now half mv square, see, when I write kinetic energies of these two, for this 6 body we have written half 6 v square, but for body 10 we have written half 10 into 2v whole square. Now the one additional point we have to remember in this type problem is when string is complicated, what we have to remember is distances traveled or the velocities gained are in the inverse proportion of the pulling tension. So since B is moved by half the tension of what A is moved, its velocity and its distance traveled is double of A, and that's why this 0.8 and 2V. And then it's simple because you can solve for V and you get the velocity. Thank you.